Two-sum. Did you know the two-sum problem is one of the most frequently asked questions in interviews at companies like Google, Amazon, and Meta? It's a classic from the Pattern Mastery 100 list, and over 30% of candidates stumble here, not because it's hard, but because it tests how you think under pressure. If you can master two-sum, you'll unlock a pattern used in dozens of top tech interview questions. So, let's crack it together. Let's break down the two-sum problem. We're given an array of integers called nums and a target integer called target. Our job is to find the indices of two numbers in nums that add up exactly to target. Each input will have exactly one solution, and we can't use the same element twice. Let's assess what's tricky here. A brute force solution would check every pair, O(n) squared time complexity. That's too slow for big arrays. We need something faster. Here's a key insight. As we scan the array, we can use a hash map to record the numbers we've seen so far and instantly check if the complement, target minus current number, is already present. That gives us O(n) time and O(n) space. Now, let's structure our approach. We'll create an empty dictionary to store numbers and their indices. As we loop through the array, for each number, we'll compute its complement. If that complement is already in the dictionary, we return the pair of indices. If not, we add the current number and its index to the dictionary. Let's try to implement it using solution 1. We're creating a function called two-sum that takes an array nums and a number target. We create a map to store each number and the index where we saw it. We walk through the entire array, and for every number nums I, we store it in the map with its index I, so we can quickly look up where a number exists later. That finishes the first pass. Now we walk through the array again, this time searching for a matching pair. For each number, we compute the number we need to reach the target. This is the complement. Target, nums I. Now we check two things. Does the complement exist in the map, and is it not the same index as I so we don't use the same element twice? If both checks pass, we return the two indices, the current index I, and the stored index of the complement. That's the end of the function. Time complexity is O(n) because we scan the array twice. Space complexity is O(n) because the map can store up to n elements. Let's verify solution 1 for two-sum. Input is nums equals 2, 7, 11, 15, and target equals 9. We first build the map. 2 maps to index 0, 7 maps to index 1, 11 maps to index 2, and 15 maps to index 3. Now we start checking. At I equals 0, the value is 2, so the complement is 9 minus 2, which is 7. 7 exists in the map, and its index is 1, which is not the same as 0. So we return 0, 1. The output is 0, 1, and the expected is 0, 1. They match, so solution 1 is correct for this test case. Let's try to implement it using solution 2. We're defining a function called two-sum that takes an array nums and a number target. We create a map called num to index to store numbers we've already seen, along with their indices. Now we loop through the array from left to right. At each index I, we calculate the complement, which is target, nums I. This is the number we need to pair with the current value to reach the target. Next, we check if this complement already exists in the map. If it does, that means we found the earlier number that completes the target, so we immediately return the pair of indices, the stored index of the complement, and the current index I. If the complement is not in the map, we store the current number nums I, in the map with its index I, then continue. If we finish the loop, the function ends. Time complexity is O(n) because we only scan the array once. Space complexity is O(n) because the map can store up to n elements. Let's verify solution 2 for two-sum. Input is nums equals 3, 2, 4, and target equals 6. We start with an empty map. At I equals 0, the value is 3, so the complement is 6 minus 3, which is 3. 3 is not in the map yet, so we store 3 mapped to index 0. At I equals 1, the value is 2, so the complement is 6 minus 2, which is 4. 4 is not in the map, so we store 2 mapped to index 1. At I equals 2, the value is 4, so the complement is 6 minus 4, which is 2. 2 exists in the map, and its index is 1. So we return 1, 2. The output is 1, 2, and the expected is 1, 2. They match, so solution 2 is correct for this test case. Alright, let's quickly recap two-sum. This one looks simple on the surface, but it's a great test of whether you can spot an efficiency upgrade and apply it cleanly. We're given a list of numbers and a target value, and the goal is to find two numbers whose sum matches the target exactly. What makes this problem so common in interviews is that it checks more than correctness, It checks whether you can connect a straightforward idea to a precise, reliable strategy. We consider the brute force approach and recognize the main issue. It becomes too slow as the input grows. The key insight was realizing we can track what we've already seen using a hash map, and then instantly check whether the matching complement exists. That shift is what takes the solution from quadratic time down to linear time. The plan follows a simple loop-driven flow. For each number, compute the complement needed to hit the target, then check if that complement has already appeared. If it has, we immediately have our pair. If not, we store the current number and move forward, relying on fast lookups to keep everything efficient and organized. We implemented that logic exactly as planned, and it ran successfully on LeetCode without errors, with the hash map tracking values in real time and the complement checks naturally guiding us to the correct pair. We verified correctness using LeetCode test cases, including cases where the expected indices matched perfectly, like returning 0, 1, 4, 2, 7, 11, 15, with target 9, and 1, 2, 4, 3, 2, 4, with target 6. The results confirmed the strategy worked efficiently in linear time with minimal extra space. The biggest takeaway from 2Sum is that the solution isn't about complicated math, it's about choosing the right tool to reduce repeated work. Once you internalize the complement and lookup pattern, you start recognizing it everywhere, and it becomes a foundational habit for building faster, cleaner solutions under interview pressure.